In this lesson, we introduce the ideas of average and instantaneous rates of change and show that they are closely related to the slope of a curve at a point on the curve. But first, let's review slopes of lines. Given any straight line, we can find the slope of the line, which is a measure of how steep the line is, if we are given 2 points on the line. So for example, if we know the point x1 comma y1 is on the line, and we know the point x2 comma y2 is on the line, then we define the slope to be the difference between their y-coordinates, this vertical distance between the 2 points, divided by this horizontal distance, the difference in their x-coordinates. The change in y-coordinates can be written as y2 minus y1. Change in the x-coordinates can be written as x2 minus x1. Therefore, the slope of this line, usually denoted m, equals y2 minus y1 divided by x2 minus x1. So this formula, the slope formula, will work if you know at least 2 points that are on the line. But we shall see it's actually calculus that helps us find the slope of a line if we only know 1 point. Now let's define the average rate of change of a function over a closed interval. If you have a function f of x, then the average rate of change of the curve y equals f of x over the interval from a to b is given by f of b minus f of a, all divided by b minus a. This is often denoted the difference in y divided by the difference in x. And as we shall see, this is actually equal to a slope of a line. So given the curve for f and 2 points on the curve, let's say this is the point a comma f of a, and given another point on the line with coordinates b comma f of b, then consider the slope of the secant line that passes through these 2 points, which is this line right here. Well, if we look closely, the y2 minus y1 over x2 minus x1 slope formula will give us exactly the quantity f of b minus f of a over b minus a for the slope of this line. So we see that the average rate of change over a closed interval is actually equal to the slope of the secant line that passes through the points a comma f of a and b comma f of b. Now let's talk about the slope of a curve at a point. We know what is meant by the slope of a straight line. In fact, we have a formula for the slope of a line passing through 2 known points. But what does it mean by the slope of a curve at a point on that curve? If there is a tangent line to the curve at a point, which is a line that just touches the curve at that 1 point, then it would be reasonable to identify the slope of this tangent line as the slope of the curve at that point. But we need a precise way to find the slope of this line. Since this tangent line just touches the graph at 1 point, we can't use the slope formula. But the slope formula still helps us because we can estimate the slope of this tangent line by considering the slope of a secant line that's near this tangent line. Consider this secant line passing through the point P and a nearby point Q. If Q is very close to P, then the slope of this secant line will be a very good approximation for the slope of the tangent line. We will assume that we know the coordinates for both points P and Q. Therefore, we can use our slope formula to find the slope of this secant line. Then we will investigate the slope of these secant lines as Q gets closer and closer to P. We will investigate the limiting value of the secant slope as Q gets closer and closer to P along the curve. We will clarify the word limit in future lessons. But if the limiting value of this secant line exists, then we will define the slope of this tangent line to equal this limiting value of slopes of secant lines. So we define the slope of a curve at a point to be equal to the slope of the corresponding tangent line at that given point. Earlier, we saw that the average rate of change of a function over a closed interval equals the slope of a secant line over that interval. Now we can define the instantaneous rate of change of a function to be also equal to this slope of this tangent line. In summary, we see that rates of change of a function can be identified as slopes of lines. The average rate of change of a function over an interval is equal to the slope of a secant line. The instantaneous rate of change of a function at a point is defined as the slope of the tangent line at that point. So we see that instantaneous rates and slopes of tangent lines are closely connected. In future lessons, we will investigate this connection thoroughly, but we will first need the concept of a limit.